Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello and thank you for joining us on the podcast we affectionately call Space Nuts. And my name's Andrew Dunkley, your host. And with me as always is astronomer Fred Watson. Hello, Fred.
Hello, Andrew. I wasn't aware that we were affectionate towards it.
Well, we are this week.
Okay.
That might change. It might change like the space weather. We're going to talk about
absolutely.
something that's popped up on their website in regard to a sunspot. They actually do publish a lot of information about sunspots on a regular basis because the sun has such a big impact on the weather around us and the weather in our solar system. But this one's interesting. It's a reverse polarity sunspot. So we'll talk about that because that's a little bit out of the ordinary. Another thing that's a little bit weird is water vapor from a protostar in the Cat's Paw Nebula. Nothing to do with Mandu, but...
Who's asleep on the lounge at the moment?
He's asleep every time we talk about him.
Yeah, he does sleep a lot, I have to say.
Yes, well, that's what cats are good at. And a question from Aziz in Uganda, who has brought up a topic we have discussed before, but it's a fascinating subject simply because it is a big problem for longitudinal space travel, and that is the effects of microgravity. And how we get around that. So we'll revisit that particular problem. But first of all, a reverse polarity sunspot. Please explain.
Well, the first thing about this sunspot, it's really a sunspot group, as all sunspots are, and it's very big. And it's big. That's a surprise because we are at the moment at what we might call solar minimum, which is the sort of minimum period of the sun's activity. Remember, the sun goes through this 11-year cycle. Mm-hmm. In fact, it's actually a 22-year cycle for reasons that I will explain in a moment. But this particular sunspot, I think it appeared about a week ago, a little bit more perhaps. It's designated AR 2720, which is a nice number. Yes. It's as good as any other. But yes, it is not only large, and it's certainly bigger than the Earth, but it's odd in that, exactly as you've said, it's a reversed polarity sunspot. And the bottom line here is that the sunspots which we see occur in pairs, usually one to the east of the other. So they're kind of horizontally in pairs. They're not vertically or in pairs along a line of longitude, if I can put it that way.
Yeah.
So they sit along a line of latitude. And actually their positions change throughout the solar cycle as well. The latitude of sunspots alters. But we're not talking about that at the moment. What we're talking about is the fact that when you've got a pair of sunspots like that, an easterly and westerly ones, they have basically their own magnetic fields, which are different in the sunspots of the pair. How do we know about magnetic fields in sunspots? I hear you ask.
I was just thinking that.
You get a big magnet, and stick it as near as you can to the sun, and see which end is attracted. No, you don't. There's a technique called Zeeman spectroscopy. And what it is so we've talked about the spectrum before, the fact that if you take starlight or light from the sun, split it up into its component rainbow colors, we find that if you do it properly, there is this barcode of actually usually dark lines imprinted on it. And those dark lines are what we call absorption lines. They correspond to the light of a particular element in the atmosphere of the sun or the star being removed by that element. It's a complex process, but they're called absorption lines because the element absorbs the light. And so you've got this imprint on the light of the sun, which otherwise would be a completely featureless rainbow spectrum. It imprints this dark line on it, and there are different patterns of dark lines for different elements. In fact, the sun spectrum is incredibly complicated because it's got so many of these dark absorption lines on it. That's a long way round of introducing this idea of Zeeman splitting, which is a phenomenon which was recorded by, I think he was Dutch actually, Herrn Zeeman, Z-E-E-M-E-M-A-N, I beg your pardon, Z-E-E-M-A-N. I beg your pardon, Z-E-E-M-A-N.
Depends which part of the planet
That's right.
you're talking to.
I was talking to a colleague from the United States a couple of weeks ago who said, "What's Z?" "Oh, you mean Z? Yay, great stuff." Anyway, Zeeman. So the phenomenon is that if you pass the light through a magnetic field, it splits the absorption into two. They're very, very finely separated. You need extremely high precision equipment to see it, but you can tell from that what the polarity of the magnetic field is. And so that is how the scientists know that this set of sunspots, which has North Pole and South Pole ends of the magnetic field, they're actually backwards way round compared with what they ought to be.
Do they know why?
Not yet, but there's a good hint coming up. So you've got the pairs of sunspots which show opposite polarity, and now I can't remember which way around this is, but normally one is north leading, so north's coming first. But then, and so all your sunspots in one solar cycle would have north leading. But then when you go to the next solar cycle, the next dollop of 11 years, the polarity reverses and you get south leading. So by leading, I mean in terms of its rotation around the sun.
Right.
So what we're seeing here is one whose polarity corresponds not to the present solar cycle, but to the next one, the one that's coming up.
Okay.
And that's why I said that actually the solar cycle is 22 years, because you've got 11 years with one direction of magnetism and then 11 years again with the other direction of magnetism. So altogether, that gives you this 22-year cycle. So what's happened is we've got to the end of it. They're all numbered, actually, since they were first observed.
Yeah.
Now, the one that we are observing at the moment is solar cycle 24. If you multiply that by 11, it'll tell you how many years we've been observing them. It's rather a lot. But it looks as though, because this sunspot pair has its polarity reversed, that this might be the first sunspot of solar cycle 25. In other words, it's the start of the build-up to the next solar maximum, because we've kind of gone through a solar minimum. It does tend to happen that at the interface between one solar cycle and another, you will get this mixing up of the polarities. But it's a hint that we are either approaching or certainly very near the minimum of the solar activity. And slow transition from solar cycle 24 to solar cycle 25 seems to have started.
So to use a very rudimentary example, this is like a change of season for the sun.
Yes, that's right. It is, because it's not to do with illumination on the surface of the ground like our seasons are caused by here on Earth. But it's exactly what it is. So the 11-year cycle has been known for many hundreds of years, but the fact that it's actually a 22-year cycle, I think, probably only goes back 100 years or so, and so it is a change in the season. Exactly so.
Okay, and is there any impact on us on this planet?
But always when you've got big sunspots, it tends to imply that there may be solar flares there. And of course, solar flares are what hurl, this wind of subatomic particles towards the Earth, and give you things like the aurora borealis. And actually, on that current space weather page, there is a beautiful photograph of what's called an auroral corona, taken from Alaska. If people have a look at the current edition of spaceweather.com, and I should just date stamp it because they change it every day. That's the 27th of August. It's the stunning picture of the aurora. So what that's telling us is that auroral activity is still relatively strong. And this sunspot kind of underlines that. It means that the sun is, even though it's at solar minimum, it's still relatively active. It's not gone completely dormant as sometimes it does in the solar minimum.
Actually, they're suggesting this geomagnetic storm was a bit of a surprise.
Yes, that's right, because we're near solar minimum.
Yeah. So there's some weird things happening on the sun, so it's probably appropriate that we're sending a new probe there to have a look, although it's not really going to be focused on these kinds of events. It's more interested in the corona, but it's just a constant amazing a constant source of amazement is our little star, isn't it?
Oh, it's sensational what we're learning about it, compared with what we knew 100 years ago, when I was a lad. It's blown us out of the water. We kind of vaguely understand now why these magnetic phenomena occur. There seems to be a lot of magnetic activity just beneath the visible surface of the sun, which of course is not a solid surface because it's a gas world.
It is indeed.
A gas star.
So we may well be seeing a change of season on the sun and moving into its 25th solar cycle. So there may be some more to report on that. And obviously from the questions we've been receiving on Space Nuts, Fred, it is certainly a source of interest for a lot of people. So no doubt we'll get to talk about it again.
I've just got a question for you, Andrew, about this. Because since the solar cycle, now I hope you can answer this, the solar cycle comes in two halves of 11 years each. Does that mean that the whole thing is a solar bicycle?
Oh, dear. With 22 pedals. I don't know.
You can edit that out if you want.
No, I'll leave it there. It makes me sound brighter than you for a change. That's why they call us Space Nuts, I'm pretty sure. This is Andrew Dunkley with Fred Watson. Now let's take a little break and find out more about our sponsor, ExpressVPN, rated #1 by TechRadar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
3, 2, 1.
Space Nuts.
Now, Fred, we're going to talk about something that's close to your heart. That is cats. There's a place called the Cat's Paw Nebula, and astronomers have discovered something a little unusual involving water vapor. What could they have found, I wonder? I'm surprised because cats traditionally hate water.
Hate water, yes, they do. They don't like water at all, especially Mandu.
Yeah.
The Space Nuts cat. I'm sure he'd be interested to know about this story, being the cat's paw story, if he could be bothered to wake up. So the Cat's Paw Nebula, it's worth hunting out photographs for it. Photographs of it, because of course, it's a nebula, so it means it's a cloud of glowing gas in space, mostly hydrogen, but with other things in it as well. But if you Google it and have a look for the photographs, you will see that it is exactly the shape of a cat's paw. Slightly odd,
exactly what it looks like.
It's a cat's paw, just from the underneath.
It is spectacular.
With no visible signs of claws.
No.
It also has, as you might expect, a fancy name, which is NGC 6334I.
Right.
Yep, that's the Cat's Paw Nebula, and it's a known source of molecules. So there are molecules in that nebula. Now, this is not unusual. There are things called giant molecular clouds, and this is probably one of them, actually, which are giant, they're very big, and they're clouds, and they contain molecules. We tell it like it is in astronomy.
Yeah, sure do.
And we think that's where, star formation is taking place in these clouds. We've all seen lots of pictures of them on the web, even though they might not be called that. And they are of great interest to astronomers who observe the sky at millimeter wavelengths. And that's radio waves with a wavelength of a millimeter or shorter, millimeter and sub-millimeter wavelengths. And of course, probably the most able telescope in the world in that wavelength regime is ALMA, the Atacama Large Millimeter Array, up at 5,000 meters there in the northern Atacama Desert. And it's owned and operated by the European Southern Observatory, which you will remember we in Australia are now affiliated to by means of a strategic partnership. So one of the astronomers at the ESO, the European Southern Observatory, Geoffrey Blake, he has observed the cat's paw with ALMA and has found that there are jets of water streaming away from the protostar. That's a star in formation deep in the Cat's Paw Nebula. So this star is actually sending northern and southern polar jets of material, which is what happens with protostars. That's what they do. And it's a similar process to what happens with black holes. Andrew, you'll remember that black holes, very energetic black holes, send streams of material actually at relativistic velocities. That means very near the speed of light from their north and south poles. And those streams, as with the streams from a much more modest object, this protostar at the middle of the Cat's Paw Nebula, they're really focused by magnetic fields. Once again, magnetism is the name of the game in today's issue of Space Nuts.
Yes.
The difference, though, here is that with this protostar in the middle of the Cat's Paw Nebula, what we're seeing is jets of not wet water, of course, it's water vapor. Water is not really a surprise. We know that water is the most common two-element molecule in the entire universe. And so it's no surprise to find it there. What surprised me a little bit, though, is that it is actually heavy water. And heavy water is made not from the normal isotope of hydrogen, but something called heavy hydrogen or deuterium. So deuterium is actually something that's also relatively common throughout the universe. Well, all right, if it's common, if by common I mean 26 deuterium atoms for every million hydrogen atoms, it's common. So it's much less than hydrogen, but it is there, and it's pretty well everywhere because it was a byproduct of the Big Bang. The Big Bang actually produced deuterium. So this particular stream of water vapor in the Cat's Paw Nebula is rich in heavy water. That's interesting because there are all sorts of links here with comets, which I'm not sure. I haven't actually had a chance to read the original paper, which is published in the Astrophysical Journal Letters. So I don't know whether these observations make the link with comets. But comets are known to have rather more heavy water than the oceans of the Earth does or do, and that's why we are now in some doubt as to whether the oceans of the world actually were filled by water from impacting comets years ago.
That is fascinating.
The amount of deuterium is different from what we find in oceans. Having said that, the only comets that we've sampled well enough to know how much deuterium there is are measured, on that. You can count them on the fingers of one hand. I think it's about 4. And I think some of them show normal water as well as heavy water. So it's a very indistinct conclusion to draw. It's certainly drawing a long bow, but it is interesting to me that there's heavy water in this nebula, the Cat's Paw.
Yeah, where's the vapor going if it's being shot out from the north and south poles?
So what it does is it actually energizes what's called the ISM, the interstellar medium, which is basically the same kind of stuff as we've got between ourselves and the sun, only we have the solar wind, which is blowing the medium out towards us. In deep space, you've got a similar thing. You've got lots and lots of protons and electrons too floating around in space, as well as some dust and probably complete elements as well, and in fact molecules. There's kind of everything out there in the interstellar medium. So when you've got these jets, what they do is they tend to pile up the material of the interstellar medium itself, almost like if you can imagine yourself with a hose pipe with a lot of dirt on a path or something, and you spray it along and you're pushing all the dirt so it clumps up or it piles up against itself. When gas does that, it tends to get shocked and it will actually start emitting radiation, and that's probably one reason why we can see some of the pores of the Cat's Paw Nebula, because of that sort of effect.
So that it's basically space hosing down the cement out front.
You've got it in one,
yeah.
Yes.
It's interesting because you look at these things and you just you're astonished by them, but you don't really understand how they occur or why they look the way they look, and being able to break it down like that is very helpful. But it's again one of those mysteries of the universe. But just reflecting back on something you said earlier, we've reached a point now where we can do analysis of certain things and look at the breakdowns of what things are made of, which gives us more and more clues as to how certain things are the way they are, and throw up questions about how we have water on Earth or where it might have come from. Or to another degree, cast doubt upon it, depending on which way you want to look at it. So it's just a fascinating science, and it's one that, as you learn, keeps throwing up more and more questions. And we're discovering that even with our audience, Fred, because that every time we talk about something, we get questions, because I suppose that's one of the frustrations of astronomy. You can't always know the whole answer.
No, we never can. I just underlining what you've said, Andrew, I think the really interesting aspect of this as well is that, yes, we kind of understand the physics of these things, in a theoretical way, but just trying to imagine, you with your head looking out the window of a spacecraft at this phenomenon taking place, a stream of water vapor molecules hurtling at high speed towards a cloud of gas and shocking it into excitement. It's really rather remarkable stuff.
And how fast does that happen, though? I mean,
well, often these things achieve what we describe as relativistic velocities, which means not far short of the speed of light.
Yeah, so pretty rapid.
It's very rapid. That's right. I didn't mention, by the way, that this Cat's Paw Nebula is quite a long way away. It's about 5,500 light years away. So we're not getting a close-up view of it, but the view we're getting is really quite remarkable.
Indeed. Yeah, it's definitely worth looking up if you want to check it out on the internet. Lots of wonderful photos of it. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Finally, Fred, a question from our audience, and we say thank you to Abdul Aziz Musa from Uganda in East Africa for this one. Aziz, it's great to have you on board. I don't know if I've told you, Fred, but we've got a handy little device now so that when we publish a new episode, I can watch a world map online and see exactly where our podcast is being downloaded in real time. And it's like the other day I promoted it heavily on various social media websites, and then I jumped straight to the map to see what was going on, and instantly 13 downloads happening simultaneously around the world. It's really quite amazing. So it's really good to be getting into Uganda. We haven't had a question from Uganda before. So Aziz has this question. To the best of my knowledge, staying for a long time in space, microgravity, has side effects to the human body, including muscle deterioration, amongst other things. So are there any current viable solutions to address this? And if not, how do space exploration programs expect to deal with unforeseen long-term microgravity exposure side effects as to be expected in future human Mars exploration programs? And before we start on his answer, this also brings into play another question we had recently, which we answered on Facebook about artificial gravity and is any development going on there, because someone's going to think of that. So maybe we can dovetail that in. But any current viable solutions, Fred?
I think there really is only one, and it's the age-old, centrifugal force solution to try and mimic it. Aziz is quite right that there are all kinds of pretty awful side effects due to microgravity. And these are now really pretty well documented ever since the Mir space program, the old... in fact, it was Soviet, I think. No, it wasn't. No, it was Russian. It was after the end of the Soviet Union. Mir, which was like a forerunner of the International Space Station. And then since 2000, we've had the International Space Station, which has been a great testbed for the effect of space on the human body. And so the two principal things are exactly, as Aziz says, muscle deterioration, but also you get the effect of bone deterioration as well, osteoporosis setting in, so that there is a weakness of the bones that's created. And you and I have spoken about other physiological effects. It affects your sight. The microgravity is known to have some rather strange effects on the retina, which may turn out to be long-term rather than things that you can recover from. So the way this is dealt with in the space station is astronauts spend about 3 hours a day exercising. I'm pretty sure it's at least as high a regime as that, on treadmills and all kinds of horrible torture devices that are designed to exercise their muscles to try and minimise the effect of this microgravity. I guess in the last analysis, though, that really the only technology that we can visualise at the moment to deal with that is what was portrayed by Stanley Kubrick back in 1968, I think it was, with 2001: A Space Odyssey, that revolving space station, where you basically have a big wheel in space and everybody lives on the outer edge of the wheel, feeling its own artificial gravity. That has never really been tested because you need some fairly serious engineering to set that up and to get the rotation at the right level. There is talk of doing things like tethering two capsules together with basically a rope or a cable, and then to set them spinning about their common center of gravity, so that the cable basically is what holds the two together. But the pair are actually rotating, and that would create artificial gravity. That's certainly something that was suggested a few years ago. But even to make that work, you actually need quite high levels of rotation, unless you're talking about very, very, very short pieces of wire. And the whole thing turns out to be something that is quite technologically demanding. So if you can fork out all the billions of dollars needed to make your spacecraft give you artificial gravity that way, that's great. There might be other slightly wonky side effects due to the fact that your view of the outside world is constantly changing.
Well, if you were looking back at Earth would appear to rotate, because
right.
you would be perceiving it from your brain. Your brain would perceive you as being not in motion, so the Earth would rotate in your vision.
That's quite right. Yes, I think that was depicted actually in 2001 in the movie. Anyway, that's you're right. You almost perhaps the most important sense we have in determining our sense of direction and which way is up and things like that is the force of gravity. It's what defines our entire existence. And so it would in space too. If you could generate artificial gravity, yes, that will be your reference system.
And if I might just add, I've interviewed a couple of astronauts in my time, and it's interesting that your perception of up can vary from individual to individual. Some of them,
yes, that's right.
Some of them say to me, my feet pointing at the Earth feels like up. Others say, no, I feel up with my head pointing towards Earth. When they're it's just a strange thing, but everybody has a different perception of it. It's bizarre.
That's right, because it's a totally arbitrary thing. It's pretty fixed here on Earth. We know which way is up and which way is down, but as soon as you get rid of the gravitational pull of our planet, you're in deep trouble because you don't know whether you're on your head or your feet. Just one extension to this is that one way that this doesn't help you is how to cope with the fact that Mars itself, if we go to Mars, only has 1/3 of the gravity of our own planet. So you're never going to be able to simulate Earth gravity on Mars because you can't do it by centrifugal force. You are basically stuck there. So we will have to deal with the problem of how humans react to reduce gravity and the long-term ill effects of it. The same is true on the moon. It's 1/6 of Earth's gravity on the moon, so you've got a similar problem. It gives you great ability to hop along on the surface.
You can break the high jump record.
Absolutely, do all of that, but that's not what the issue is here. It's all about our well-being and how good we feel internally.
Yeah. So, and yet the concept of artificial gravity seems so very simple, and I suppose that's why the question keeps coming up: why is it so hard? And as you've said, the engineering involved is just not that simple, and getting it to work on a scale where you achieve 1G for long-haul travel is obviously hard to A, achieve, and B, maintain, and then C, if you do it and you land on a planet that hasn't got 1G, I mean, there's all sorts of other weird stuff that you've got to deal with. Maybe they could work it out so that you could time it so that when you got to Mars, you lost 2/3 of your capacity as a human being, and then when you got on the surface, everything would be normal.
I think NASA's medical division needs you, Andrew, with suggestions like that.
Yeah, but you'd never be able to come home.
They'd send you to Mars very quickly.
So, yes, the people are thinking about it, but I don't think anything's actually reached a point where they've got anything to test, because it's all, it's in the too hard basket somewhere in NASA or anywhere for that matter. And as you've already alluded to, there are potential long-term side effects, and those are the things that they need to consider before they do a long-haul trip. Even then, some of these side effects, as you mentioned, the vision problems, can differ from individual to individual. Now, there might be a whole bunch of astronauts that never would suffer the problem, but then one of them might go blind. It's just one of those things amongst many.
Maybe there's some genetic research that might shed some light on that down the track. I'm sure that sort of thing is going on as we speak.
Oh, no doubt about it. Yeah, but right now, like anything to do with the well-being of humans, the answer is exercise.
Indeed it is, that's right. Which is it doesn't apply to the well-being of cats, apparently.
They don't need it. They're just naturally fit. They've got all the muscle tension and all the bits and pieces that keep them athletic. Except for that giant one I saw on the news the other day that's broken the world record for being a fur ball. But we do treat them like people, and they end up looking like us in some respects.
Yes.
Anyway, Aziz, I hope we answered your question, and thank you very much for sending it in. It is a fascinating problem and one they are yet to solve. So that one, I think, will take a while to resolve for long haul travel. It won't stop us going. It just means people will have to suffer through the effects. And we do encourage your questions. Like I've been saying recently, we're getting so many we won't be able to answer absolutely every single one of them, but we'll do our best to shovel them all into Fred's inbox, and he can deal with them. And
thank you very much. And thank you to our listeners too. I really appreciate it. The fact that you are hungry for these answers.
Yes, and the questions are amazing sometimes. They're just so, and most of the time, they're just so well thought out and intelligent, and it's a good thing to have that kind of effort put in, and gives us something really juicy to think about. Fred, as always, it's been a great pleasure. Thank you, sir.
Thank you, sir, to you too, and we'll speak again next week, I hope.
I hope so too. Fred Watson, astronomer, with us every week here on Space Nuts, and from me, Andrew Dunkley, thanks for listening. Catch you next time.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.